Okay, good morning, everyone. Bill Graham will continue the series on equivariant cohomology.
Okay, well, thank you very much. And so I wanted to say, I don't think I said this last time, but I've really enjoyed being here at this part of this wonderful program. So I just thank you for the opportunity to participate. So, okay, I wanted to just say a couple of things that where we were at the end of last time. You finished up by defining the homology and also the Chow groups. And I'll focus on the homology because I'm talking mostly about cohomology today. One thing that I mentioned was that if X is smooth of dimension n, there's this cap product from H. I mean, there's this cap product anyway, but it's an isomorphism from Hi g of X, H2n minus I g of X. Now, if Y is an invariant closed subvariety, then we have a class, say, of the appropriate dimension. We have a class Y in here, and I could decorate this with a G if I want to, although I may not remember to do that, or I may not do that, but I can. This is the G equivariant fundamental class, and so I want to call the class here that corresponds to this delta of Y. And delta is meant to think of dual because it's like Poincare dual class. So this is an isomorphism, so I can transport this over here, and this is the Poincare dual class. And I'm just doing this because I want to actually distinguish between homology and cohomology, and so I want to try and remember where things lie, because I'm going to do certain things for varieties that are not necessarily smooth. The other comment is that remember that Hi g of X was Hi plus 2 times the dimension of U mod G of U cross upper G of X. So U is our model. U is it's like E to N. And so the thing that happens here is that this group vanishes. The way the indexing, this space here actually has dimension N plus dimension of U mod G. So this vanishes. So this is 0 if I is bigger than 2n, which is the dimension of X. But it can live in infinitely many negative degrees, because as U gets big, I can be negative and this will still be positive. So, but lives, can live in I less than 0. And in fact, if X is equal to a point, we have Hi g of a point, which is Hi g of a point, is going to H minus I g of a point here. So we see that this lives in degrees less than 0, less than or equal to 0. And H0, though, is very simple. H0 g of a point is just going to be Q. Okay, so it's an artifact of the indexing, and it's okay, but I mean you have to make some choice, and this choice of indexing makes Poincare duality work out very well. So I think it's a good choice. Okay. So I want to start off today. I realized sort of when thinking about these talks that so much of this story for tori depends on the localization theorems. So I'm going to talk a lot about the localization theorems. So I'm going to say, so T again is going to be just to remind ourselves of the notation, T is C star plus D star. And so H star of T is going to be, the character group is going to be, is the span of the x1 plus the xn's, and then H star of T was the polynomial ring in x1 up to xi. And so if Tx on x I'm going to let xt be the fixed point scheme. And if x is smooth, then xt is also smooth. That's a known fact. So x smooth implies that x is. Just a remark on that. And so the main localizations here are the following. And so these theorems, by the way, I should say these theorems have a very long history. And if you look in the paper of Goreski, Kottwitz, and McPherson, they recount some of the many references. I think this version is maybe part of this is due to Chang and Shellbread, and part is due to maybe part is even due to Goreski, Kottwitz, and McPherson. I would just refer to those papers for references. So let's let I be the inclusion of the fixed point set of xt into x. And then the maps. So we have two maps here. I upper star from h star t of x to h star t of xt, and we have I lower star from h star homology become isomorphisms after inverting a finite number of elements in T hat. So what I usually write, so just to sort of say, I usually write something like I star, just to sort of introduce the notation. I'd write something like I star of S inverse of H star T of X goes to isomorphically onto S inverse of H star T XT, where S is this multiplicative set that I have to invert. It's just generated by some characters. Well, so we'll see, you know, this will be made concrete in a minute. But that's the way I would write it. That's just what I have to invert. S is some multiplicative set. And I'd say, moreover, if H star T of X is free as H star T module, which, as I've mentioned, this is true in most of the interesting examples we're going to talk about. It's true if X is smooth and projective. It's true if X has vanishing dimensional odd cohomology in the regular case. So this is true in most of the cases we're interested in. Then I star is injective, and its image can be described. And if this, I probably will be able, I'll probably say what it is later on, but I won't say it exactly this instant. Okay. So let's do an example of this. So we suggested maybe that I should do examples, and actually I just realized that in many of the talks I've gone to this semester, I've enjoyed the examples. So I'm going to do this. But of course, I can only restrict myself to simple examples. So, but I'll do like CP1 right now. So, okay, so for example, so let's start off with T equals C star. So remember here, T hat is just Z bracket X, and X is just Z times X, and X is just the character. X is viewed as the map from T to C star. In this case, X of T, it's just T. It's just the identity character here. Yes.
Right, let's ask a question
Yes,
about.
Sure.
Could T act freely on X?
Yes, and then this module would vanish after when you this would be zero in this case. Sorry. If there are no fixed points, then when you invert the characters, you can get zero. You'll get zero, in fact. You can think of that if x is equal to t itself, for example, then you're modding out in effect by all the characters. And so if you invert any of them, you get zero. Okay. So I want to say x acts on, so let x act on v equals c2 with weights. So the weights should be multiples of x. I'll call them a naught x and a1 of x. And we saw, and so then, sorry, tx on this. So then x is going to be p of v, which is just p1. And we saw last time that h star t of x in this case was just, well, it's h star of t, which is z of x, and then I throw the one indeterminate h, and then I have to modify the relations h plus a naught x times h plus a1x. That's a special case of this calculation we did last time. So here xt just consists of 2 points here. It's the coordinate points p0, which is 1, 0, and p1, which is 0, 1. And so the inclusion xt is really sort of just the pair like I0 and I1 in a sense, where I0 is the map from P0 into, this is from xt into x. I0 is from P0 into x, and I1 is from P1 into x. And so here we have h star of t of x. This is, I'll just copy it down again. Q of x here. I mean, I should q of x on q of x comma h, or h x comma h mod h plus a naught x. H 1x is going to via, so I star is just going to be then I naught star, I1 star, right? Because this is just the inclusion of the two separate components. The cohomology of the fixed point set is the direct sum of the cohomology of this piece and then this piece, because they're just two distinct points. And so what we're going to get here is h star t naught plus h star t of t1. Sorry, I know that's back a little, but this is just h star t plus h star t. So I'm just, because p0 and p1 are points. So now I have to compute what I naught star and I1 star are. So now both of these are ring homomorphisms. So let's just focus on I0. Of course, I1 will be exactly the same. So I naught star, well, it's a ring homomorphism. And it's also h star t linear, because this is like our ground ring. And so any pullback commutes with the action of the ground ring, which is just pullback from a point. So we know that I naught star of x equals x. And this, or really that's this x in this little picture here. So all we have to do is compute I naught star of h. And so I naught star of h is what? Well, this is I naught star of, so h is the first Chern class, the equivariant first Chern class of the dual S star, where S is the tautological subbundle. S star is the dual tautological subbundle, which corresponds to O of 1. So this corresponds to O of 1. So it's I naught star of C1 T of S. So that the functorial properties of Chern classes tell me that this is I naught star. Sorry, this is just it's the first Chern class of the pullback I naught star of C1 T of S. Now what this is very simple because this is C1T of just the fiber S star at the point P naught. The fiber of S star at P naught is just a vector space, which is a one-dimensional representation of the torus. And that's what this vector, the restriction of this vector bundle to that point is just this representation of the torus. And this here, now this is the dual representation to the representation which has weight A naught X, because it's on the first coordinate. So therefore this is minus A naught X. And so, by the way, just to sort of comment, when you're dealing with things with vector bundles and fixed points, many of these restrictions that look sort of potentially intimidating, these kinds of pullbacks can be calculated just by looking at what the torus action on the restriction of the vector bundle to the fixed point. So actually, these kinds of restrictions that occur are typically easy to compute, or relatively easy. So in any event, what we see here is we conclude that this point here takes, let me just write down here what our conclusion is. So we saw that X here goes to the point X comma X, because I said I naught star and I one star of X is X. And H is going to go to minus A naught X minus A1 X. Both, now we see, I should have said that A naught is not equal to A1. That otherwise the fixed action would be trivial. In this case, you can see that if you invert X, this map becomes an isomorphism because both of these modules are free modules of rank 2, and this is an invertible matrix. So if you invert X, I star is an isomorphism. Okay? Any questions on that? Okay, well now let's look at I lower star. So we have I lower star from H star T of XT. And this is going to to H star T of X. Now this is the direct sum of H star of T of P naught plus H star T of P1. This is I star again. So this is really, this is really I naught star, I1 star again, just like before. I split up into these two pieces. Now, the thing to say, by Poincare duality, this is equal to the cohomology applied to P naught, the cat product. This is Poincare duality. This is a smooth space. This is the cohomology times the fundamental class of this point. And this again is the cohomology times the fundamental class of this point. This map is linear over H star of T. So I only have to figure out where P naught and P1 go to. So, so then,
Sorry, if you split the T and this star, you
because this is cohomology, this is time, this is like a cat product here. So remember by Poincare duality, that's a cat. However, I actually don't want to tell you right now. I have it in my early list, but I don't want to tell you right now exactly what these do go to. But instead, what I want to, because I want to focus on some other. Well, yes.
All right, can you repeat, what was the thing you said about when A naught equals A1?
Oh, when A naught equals A1, the action on projective space is trivial.
Oh, okay.
So I couldn't invert this matrix, but on the other hand, this wouldn't be the fixed point locus, so the whole calculation kind of falls apart. Anyway, so I'm not going to tell you in terms of these generators what P naught and P1 go to, although I can if you want to, if you really wants me to, I can, but instead I want to tell you something else. So H star, it's going to turn out that H star, but here, maybe this was what you were talking about. Here I should have put but if that's what you were talking about, that's what I should have put. Yes, thank you. So So here, what I'm going to tell you is that H star T of X, it's free with basis. It's free over H over the ground ring with basis. I can take as a basis given by P naught, the fundamental class of P naught, and the fundamental class of X. I can decorate these with T's if I want to, but I think I'll just avoid an extra subscript. Or, I mean, this isn't the only basis, or P1 X. This is, if you like, a Schubert basis. This is a Schubert, for these things. This comes from, it has a paving by affines, and it's easy to see that this is a basis over this. So if I wanted to show that I star was surjective at least, so clearly I naught star of P naught, it's P naught, that's just that's the definition. And I naught, except as I said last time, here we're viewing P naught as a class on itself, and here we're viewing P naught as a class on X. And here we have I naught I1 star of P1 equals P1. So that's okay. But in order to show at least that this is surjective, I have to tell you how you can get X in the image of these two things. So I'll tell you this answer now, and I will justify it a little bit later. So in fact, the class X is equal to 1 over A1 minus A naught times X of P naught plus 1 over A naught minus A1 X times P1. So if you believe this, actually, you could figure out sort of what the images of P naught and P1 are. I've told you enough information to figure that out. Okay, and this is, and maybe I should put an I naught star here. Just, it doesn't, this I naught star is optional, and I1 star are optional here, depending on whether I psychologically want to think of them as living in on X or on P1. Okay, now the comment here is that this is a little strange because these here are rational functions of degree -1, but that's the way it has to work. This is a degree 1 class. This is a degree 0 class. If I want to get a degree 1 class from a degree 0 class, I have to cap it with something of degree -1 because capping lowers degree, or capping does degree by the negative. So that's the, and these coefficients here, we're going to see them in a later guide in a few minutes, but these are what we're going to call equivariant multiplicities. This will be denoted EP0 of X. And this will be what's called EP1 of X. And we'll say a little bit more about them later on. But that's what they're what is called equivariant multiplicities. Okay?
Degree of X is 1 or
Degree of X, the degree of X, this is a homology class. So the degree of X is 2n actually. So it's n if we do dividing by 2, but it's a 2n dimensional real class. So I always want to divide degrees by 2 because everything's even here, but the dimension of X is n, so it's a 2n dimensional homology class. In cohomology, it's a it's a 0 dimensional class. So the class delta X is 1. That's the Poincare dual class. And that's degree 0.
are we showing that I push forward is surjective or I push?
We just showed that I push forward is surjective now. I haven't showed that quite sure that it's an isomorphism, but you could do that.
After inverting X?
After inverting X, right, because this is a free module with this basis. We can certainly get P naught and P1 in the image, so all we have to do is get X in the image to show that it's surjective, because this map is linear with respect to the ground ring. And I've just shown how you can get X in the image, so therefore you can get a basis in the image of I star, so therefore I star is surjective.
It's not surjective before inverting.
It's not surjective before inverting. That's right. It's not this localization theorem is not true without inverting.
But I upper star is injective before inverting.
I upper star is injective. Yeah, I don't actually know if that's right. When I was preparing my talks, I was trying to think, do I know if it's as good as a description of I lower star image, and I don't offhand. So that's right. I upper star is injective after before inverting this, right? I'm not so sure about, I think it's not true that I lower star is injective if after inverting, because there'd be a relation between P naught and P1 here, in fact. So I'm not quite sure what a good description is. So yeah, that's right. I didn't tell you, I left that I lower star in that moreover. Other questions?
So you can multiply x to this equation, right? So you know the image of the two push forward, and if you take sum, it's just the idea of x.
Well, yeah, I guess in this case, I guess the sum of the push forwards is probably just, maybe it's just maybe the image is just. Yeah, I think that's right in this case, but I'm not sure I'm not sure if that's true in general, so. I mean, there's probably something one can say, but I don't. Okay. Anyway. So I want to briefly talk about localization in Schubert calculus, so just how this sort of helps you in a number of ways. So again, so I'm going to let, so now let's let x be equal to G mod B, where again, G is to be thought of as GLN, B is the lower triangular, and T is the diagonal. And W is Sn, which is the permutation matrices. Okay, so in this setting, xt is just the set of cosets WB. This is in G mod B, which is X. So this is a coset, or it's a point. I'm going to just call this point PW now, just to sort of distinguish it. And that's what the fixed point locus is. There's a finite set of fixed points in here. And so then, we have I star is really like the direct sum of IW star. IW, this goes via IW into X. So it's really the direct sum of these IW stars from H star T of X to H star T to the direct sum of these PWs, which again is just the direct sum of H star Ezo point. Okay. And so now the Schubert cell is just the d orbit of the point PW, which is called, denoted oftentimes XW naught. It's just isomorphic. It's isomorphic to an affine space. The dimension is the length of W. Probably everybody here knows what the length of W is, but if you don't, you can take this as a definition of the length of W. And the closure, the Schubert variety, it's the closure of this, which is XW. And so then the important fact is that H star T of X is free over H star T with basis delta XW. Okay. Now, on the other hand, if I, so S inverse, so S is some indeterminate set. I can, if I want to S, I can invert every single character I want, every single character, and that's fine. There's no restriction. So S inverse H star of T of X Well, it still has, this is still a basis, but it has another basis as well. Has a second basis. Namely, Poincare dual classes of the points PW. Now, why is this a basis? The localization theorem tells us that, in fact, so if you, the reason is that if you look at, so the reason this is a basis is the following. Suppose I take I of U star of delta of P of W. So I pull this class back via the inclusion to the point PU. So if U is not equal to W, this class is zero. This pullback is zero. I mean, just sort of morally speaking, this is like an intersection of some classes, and U and W, PU and PW, if they're not equal to each other, they don't intersect, and this pullback is therefore zero. If they do intersect, if U is, in other words, if U is equal to W, what this is C, it's the top Chern class of the tangent bundle at PW of X. That's a represent, and I'll tell you, in fact, what this Chern class is in a minute, what these classes are shortly, but this is a representation of the torus, and so I can take it as an equivariant top Chern class. And this follows from what's called, the self-intersection formula. So what this means, stuff. I wounded myself on the blackboard. So no, it's okay. It's actually when I was one time in Georgia, we had to remove some of these things here because they were too deadly to the speakers. Anyway, so if you look at what I star of, if you look at I star of H star K of X, the H star to the direct sum over these H star T's of PW, say, what this is, if I take the class of PW, what this goes to by this remark here, goes to zeros in every coordinate except one. And so the image is if I invert all these things, I get a basis on this side. And therefore that's a second basis for this thing after I've inverted all of these things. And as I said, I'll tell you what these are shortly, but so the point is that, okay. Now the point is that multiplication, so I have two bases here. Now multiplication, so maybe I should say one problem, the problem of Schubert calculus, really, because this is a basis here, the Schubert classes are a basis, we can write the product delta xu, delta xv, as the sum of C of u v w delta xw, where the cu and vw are in our ground ring, H star t. And in a sense, the problem of Schubert calculus is to compute these or to understand these better. So in fact, localization gives us a method of computing these things. Because since we have two bases, well, maybe let me make a first remark. So in the basis, delta of PW, multiplication is very easy. It's really just the self-intersection formula again. If I do delta PU, delta PV, that's zero if U is not equal to V, and it's equal to C top, Cn, T of TPW X if U equals delta PU if U equals B. So the multiplication in this basis is very easy. On the other hand, so in principle, then I have a change of basis matrix. So I can write delta x u equals, let me just try and keep the notation in my notes here. It'll be the sum over v of a u v delta of p of v. And I can also write delta of pu equals the sum of b u v delta of x v, right? And the a's and b's are now, they're rational functions. They're not polynomials, but they're functions in the ground ring. And so if I can compute the a's, well, so here the B matrix is just the inverse of the A matrix here. Now, if I can compute the A matrix and the B matrix, then I can compute the Schubert constant, the structure constants CUVW, because I just convert my elements to the PWs, multiply there, and then convert back to the XWs. So if I can compute A, and then I can compute B, I can compute C of U V W. But in fact, the A's are very easy to compute. And again, it's so that everything here is relying really just on the self-intersection formula. The fact is that A UV is equal to, it's just I V star of delta of XU over, of course, our CN T of TP U of X. And the point is that, and the proof is that what we're trying to show, so by definition, we're trying to show that delta of XU is equal to the sum over V of IV star of delta of XU over CN T of T. I think this should be a V here, actually. Sorry. EB of. That's what I want to. That's at times delta of PV. That's the definition of the change of basis matrix. That's why I want to show it, because then this will be the same as this. If I apply IV star to both sides and use the self-intersection formula, I get exactly the result, because this will vanish except for one term, which will be exactly cancel out of this. So apply IV star to both sides and use self-intersection. Okay, any questions on that? Okay. Well, now I'm going to tell you so again, I mean, as I said, I realized that I can do so much with localization. The next thing is that, in fact, so now we've of Schubert calculus, in a sense, to the problem of computing these pullbacks here. We have to be able to compute these. If we could compute those, then we could compute so now the problem is, well, is compute I V star of delta of X delta of X. Now, there are several ways that one can do this. I'm just going to explain, explain one way right now. And I'm going to I'm going to relate this to a different problem. So a related problem, a problem that turns out to be related. The related problem is, recall that H star T of X was equal to this R tensor RW R, where R was H star T, which is Q going X1 to N. And so R tensor WR, RW R was this polynomial ring in the X's, Y and the Y's, modulo the relation EI of X is equal to EI of Y. Okay, that was what R was. So the related problem then is, can we find an expression in the X's and Y's, a formula for a delta of XU? So, well, maybe we can try that related. So the related problem is, the question is there a formula in the X's, Xi and the Yi for delta of X? So the reason this is useful to us is that if we had such a formula, then it's not too hard to see. You see, IW star from R tensor R W, RWR, this is H star T of X. H star T of a point which is just R, this is actually easy to compute. Because IW star, yeah, I mean, it's probably, to be consistent, just be IB star. So V is, but it doesn't, I mean, V is just an element of W. So IV star, so if I have it as in terms of R1 tensor R2, so R1 is to be thought of as in the X's and R2 is in the Y's. Well, what is this going to be? Well, this picture is a little bit asymmetrical, but the H star T module structure is on the first factor of R here. So that means that this R1 is linear, so it's got to be R1 times whatever happens with the second factor. Well, there's only one thing that could really be done with the second factor. The element V is an element of the Weil group, the permutation group. It acts on this ring, and I have to apply V times V to that element R2. And that's actually the only sensible thing it could be. It's easy to check this because it's again by restricting vector bundle. You really, to calculate this pullback, you're restricting one of these tautological bundles to a point, and that's what that amounts to. So if we had this formula, then we could compute these pullbacks, and then we would have solved the problem of Schubert calculus, in principle. Now, Fulton and Pragaj and some other people were very interested in finding these formulas, and they made the following realization, which is that to find a formula, so the smallest Schubert class, so let's just let one be the element in the Weil group. It's the identity element in the Weil group. So the Schubert variety X1, it's just the point P1. It's the unique B fixed point. And what Fulton realized was that it's enough to find a formula for delta of X1. Because if you find a formula for delta X1, then there are operators called divided difference operators, which I probably won't have time to talk about today, which you can find all the other formulas for. So it's enough to find a formula for this this one and then apply. Okay. Okay, so I'm gonna keep you in suspense for a minute. I'm gonna say something, we're gonna need to use the self-intersection formula again, but I need to tell you now finally what the weights on the tangent spaces are. So remember, so we're in G is GLN. And so the characters, the weights, the roots are the characters of T on the Lie algebra of G. And this is just some set, it's the set of X, it's a set of characters, it's the set Xi minus Xj, where I is not equal to J. That's often called capital Phi. And then the positive roots are Phi plus, where we just impose the condition that I is less than J among the set of roots there. Okay. So the tangent space at the identity of X is isomorphic to the space of strictly upper triangular matrices. And that's because I've modded, B is the lower triangular matrices, so I've modded out by the lower triangular matrices, and the strictly upper triangular ones are the isomorphic to the tangent space. And the characters of T acting on this are the positive roots. So therefore, so the characters of T on T of 1B X are just the positive roots. And the characters, if I do it on a point T of V of VB of X, well, it's just the permutation V applied to the set of positive roots. So this is just V applied to 5S. So those are the characters of the representations there. So now what the self-intersection formula tells me, so let me just tell you what the answer is. So I claim is that delta x1 is equal to the product over I less than j of xi minus yj. So now, by the way, I just should emphasize this formula is not a unique formula. There are other formulas because there are relations in this ring, but this is one formula in this ring nevertheless. Okay, so the proof, well, I1 star of delta x1 is equal to it's equal to the top term class of the tangent space at 1b of X, because that's just the B fixed point. And this is just the product of the positive root. So this is just the product of I less than j of xi minus xj. I1 star of the product of xi minus yj is just the product of xi. And then I have to apply the identity permutation to the indices here. That just doesn't do anything, so that's xi minus xj. So that's the same, they're equal. On the other hand, if I look at I V star of delta x1, for V is not equal to 1, V is not equal to the identity, this is 0 by my self-intersection formula, or just by the non-intersection. On the end, I V star of xi minus yj of the product is equal to the product of xi minus x of v of j. And if V is not the identity permutation, two of these will have to be equal, and Vj will have to be equal to I for some I, and that will be 0. So that's a very simple proof of what we have now. In principle, solved the formula, the problem of Schubert calculus for GLN. Now, a couple of quick comments. Are there any questions first? Well, a couple of quick comments to make. So Fulton started, and Pargash as well, they looked at this for other groups and they wanted to find expressions for this for other groups. This method is actually not so helpful in finding an expression. It's very good in proving one, however, if you have it. And so Fulton did come up with formulas in the other types, and then this kind of method can be used to prove those formulas very quickly. In fact, although Fulton's proof was rather different, but in fact, he kind of did the algebra that's needed to check this very, very easily. So you can actually verify these formulas in the other types.
Maybe you should also mention that.
Well, that's right. Probably the main thing he did was to try and figure out what a formula is, but he was thinking in terms of like projective bundles and various kinds of bundle Turing class formulas. He wanted some kinds of formulas in terms, and he
This was a top Turing class calculation for him.
For
the class of a point was a top Turing class.
Yeah, but that's not the way he proved. This isn't the way he actually proved his formulas. Well, I don't think so. I don't think he did it this way. Let's put it this way.
Not this way. No. With the top, yeah.
Oh, but he did it with the top Turing classes. Okay.
That's what I'm saying.
Okay.
Not this way.
Okay.
You should also mention last point, Schutzenberger here. I mean, they had these double Schubert polynomials.
Right. So the other thing is that, right, there's these, it turns out, that if you pick this, if you pick this representative, then the polynomials you get with the divided difference operators are particularly nice, and they're called double Schubert polynomials, except that possibly sometimes people will reindex this yj will be like yn minus j or something like that, but they're particularly nice representatives and they have nice combinatorial properties. And in fact, there are not, what happened was that there are not as good representatives in the other types, was I think a disappointment. Okay. So my next topic is the integration formula. If we're going to take a break for 5 minutes, I could take a break now, and since it's 5 before the hour, and then I'll do that last time. So I want to talk about the integration formula. And it's closely connected to what we'll see as the Bott residue formula. And I think actually this is one of the reasons for kind of the resurgence of interest in equivariant cohomology, was that in the 1980s, there were 2 papers that came out, one by Berlin and Verne, was one paper, and the other was by Atiyah and Bott, who had a beautiful paper called The Moment Map in Equivariant Cohomology. And in that paper, they explained how localization could be used to give a very in equivariant cohomology could be used to give a very simple proof of the Bott residue formula and how it was connected with the moment map and so on. And so I think that was in a way one of the starts of the resurgence and interest in equivariant cohomology. So now I'm going to actually give kind of like one issue, which is maybe more or less important depending on your point of view, is that if you do this formula in cohomology, you're kind of restricted to smooth varieties. And if you set it up in homology, you can have something which is actually valid for singular varieties. So I'm going to set it up in a kind of a homological way today, and then we'll do that. Okay, so the general setup is the general problem is, say X is n-dimensional and complete. And so again, I'm going to just let pi be the map from X to a point. And so we have some element phi in H star of X. And we want to compute, you can think of this as, if you like, as a differential form of degree 2n. And we want to compute the integral over X of phi. And we'd like to figure out a way to do this. And so from my point of view, we can think of this homologically. We can think of this as, we can take the class of phi, which is a cohomology class, we cap it with the fundamental class of X, and then we push this forward. This becomes now a homology class. This is in H0 of X. We push this forward to something, and we get something in H0 of a point, which is just Q times a point. So from a homological point of view, that's how we can think of integration, as carrying as the cap product followed by the proper push forward. And now we have, again, I said we have the forgetful map, H star T of X, H star of X, and we have phi sitting inside there. So under favorable circumstances, we could upgrade phi to be an equivariant class. Now I could decorate this with a T, but let me just call it phi again. And so if we can upgrade to an equivariant class, phi to be an X H star of T of X, then we can use localization. So let me explain what happens in the case where xt is finite, and then if xt is not finite, then there can still be something, but it's a little bit more. It's not really very much more complicated. Okay, well, all right, so by localization, well, suppose, as I said, suppose xt is just, it's finite, it's the union, it's a set of just some t i's here. So then we can write, we have the inclusion, say, ik from pk goes into x. And so by localization, we can write x as the sum of I pk star times the class of pk. And there's some coefficient that goes in front of this. And the coefficient, you saw this is so what epkx is, it's a rational function of degree, well, it's degree minus the dimension of x. Remember, the generator has degree 2, but so as a polynomial, I mean, I don't know, you can put a 2 here if you like. It's got x to the power, it's got variables to the power minus the dimension of x, but each of the variables lives in degree 2. So we can write x in this way. So therefore, the integral of phi capped with x is just going to be, it's going to be pi star of the sum of phi capped with epk of x times of capital X times I pk star of pk. Okay. Now, this epk is not going to matter at all, but But the point is, this is a commutative ring, so I can move this phi over to the in front of the IPK star. And then by the projection formula, I can even move this past the PK star. So this is going to be pi star of the sum of, in fact, maybe I'll even put the pi star inside here. It's going to be pi star, the sum of pi star of EPK of x times IPK star of IPK star of phi back with now. This is looking a little abstract, but what I'm doing here is this EPK is actually a scalar in this picture, so I'll just move that out in front because it's in our ground ring up to inverting. So it's EPK of x times pi star IPK star of IPK star of phi capped with a point, capped with k. Okay. Now, again, this is now a scalar. I've pulled it back to a point, and this is the kind of thing we just figured out how to compute. We computed like IP star of h was like minus a naught x or something. So this is something, this is a scalar. So this can be pulled out in front as well now. So this is because pk is just a point. So this is going to be the sum of I pk star of phi times e pk of x times pi star I pk star pk. Now what is this? We have pk going via I pk going into x, and then this is just going via pi into a point. That's just an isomorphism. So this is just the sum of I pk star of phi times e pk of x times the class of points. Well, this is our integration formula, and let's take a look at it for a second. So for degree reasons, this is an element in H0 of, just think of where this is. This is by definition push pi star of phi capped with x. And this is in H0 t of a point, which is just q times the class of a. The zero-dimensional homology is just the class of a point. So this is just going to be a rational number times the class of a point, and my answer then the integral is just really that rational number. Okay, so this is the integration formula. Now, however, I've done this in kind of the wrong order in a sense, because I haven't told you how to compute these EPKs of x's. So, but this at least should serve for some motivation. In order to run the integration formula, we have to compute EPK of x's, and then we'll be able to do these integrals. And I'll make this very concrete and do an example for you. So how to compute EP of x. And so again, so the term that I'll use, these are equivariant multiplicity. Okay. So the first way to do this is if x is smooth at P, based on everything we've done so far, you could probably guess what this has to be. Everything boils down to the self-intersection formula in this case. EP of x is equal to 1 over the top Chern class of the tangent space at P of x. So when I told you before that in the case where x is P1, that example with weights A0 x and A1 x, I told you that x was 1 over A1 minus A0 x times E0 plus 1 over A0 minus A1 x times P1. That was how I computed this secretly, is that I looked at the weights on the tangent space and I just plugged those in. Okay. The second way to compute these, so the other ways of computing them involve making use of what we know for smooth varieties. So the second way to compute them is if we have a resolution of singularities. So in general, if you have a proper map, or a finite map, so if y to x is finite, t equivariant, and say xt and yt are finite, then the equivariant multiplicity at t of x, and say finite of degree d, then this is going to be 1 over d times the sum of y. If I look at the inverse image of t, and I look at the t fixed points in there of e y of y. This actually follows immediately from the definition of equivariant multiplicities, because I push these forward to get y, and I push them down to x, I get d times x. So it's actually almost immediate from the definition of equivariant multiplicities that this is true. And the third way of doing this is that if I'm in a situation where I have p sitting inside I, x sitting inside, say, f of m, where m is smooth, so I have a class delta x is in the t equivariant cohomology of m. So in this case, then the equivariant multiplicity at p of x is actually, so let's call this inclusion here j. So j is the inclusion of x into m. It's going to be j star of delta x over the top term class, say x is dimension that m is m, cm t of tp m. So again, everything has to be t equivariant, and p is a t fixed point of m, finite. So, well, you can probably guess the proof. It uses the self-intersection formula. Again, it's very easy. But we saw, in fact, we can compute these, for example, for Schubert varieties. So this tells us how, this gives us a way to compute the equivariant multiplicities now of Schubert varieties as well. Because I discussed how we can compute those j star. So in the Schubert variety case, this is xw sitting inside of x here. And if we think of xw sitting inside of x there, we explained how to compute those pullbacks. Okay? So let me do one concrete example to sort of, one more concrete example.
So in 3, you're assuming there's a T action on M.
Yeah, everything here is right. So right. So this is supposed to be T equivariant. And so P is an isolated fixed point. It's closed embedding. Okay, so let me do an example here. So I'll try and so I will put my notes in the hope that I can kind of get this right. Okay, so suppose T, so well, let's just look at an example here. Suppose I look at V is equal to C4 with coordinates Z0 up to Z3, say. And I want to suppose that, so X is going to be P of V again here. And I want to look at F, I want to look at, X is not going to be PV. PV is, so PV contains X. I want to let X to be defined by the equation Z0 Z1 plus Z2 squared. In P, that's a quadric in P of V. Now this is a singular quadric because the point Z3 is not involved. So this is singular at the point P3. So what I'd like to do is I'd like to relate this to equivariant. I'd like to say do an integral over this. So the first thing is I want to set this up in a way so that everything is T equivariant. So I'm going to so the general fact is that, if F is a polynomial, suppose T acts, if T is C star, so T here is C star acts, and F is a polynomial, homogeneous polynomial of degree D, such that T will therefore act on the polynomials. I want to say that this is a T eigenvector or a T weight vector with weight AX. A is going to be some scalar weight. I'll say with CX, TX on F with weight CX. That just means T acting on the polynomial F is T because C times F. And X is the zero set of F, then the class of X is, or then the Poincare dual of X, delta of X is equal to D times the hyperplane class minus C times X. Okay. So non-equivariantly, the class of X would just be D times H, and the correction is this minus C8 CX term here. Okay, so in this case, so now what I haven't defined a T action on this, but I'll define a T action.
X is in like H2T of a.
Yes, X is an H2T of a point. That's right. So H star T is Q of X again. So, right. So I'm going to let T. So let T act on V with weights 1, or well, I'll say actually should be with weights X minus X, 0, and AX. And A is just some integer here. Okay, non-zero. Okay. Well, then my polynomial, if this is my polynomial F, that polynomial F is actually T invariant because the weights are opposite on Z0 and Z1, and the weight is 0 on Z2. So F is actually T invariant. So X Z0 squared, Z0 Z1 plus Z2 squared is T invariant. So the equivariant class of X is just going to be 2H. So now I can write X therefore as E. So XT consists of the coordinate points P0, P1, and P3 with obvious notation. P2, that's where that coordinate is non-zero. So this is going to be EP0 of X I can put the I naught, I'll omit the I naught star for now. I might put it in later, but I'll just call this P0 plus E P1 of X P1 plus E P3 of X P3. Now, P0 and P1 are smooth. So E P of X for one of these P's is just 1 over C2, the top term class of the tangent bundle of the tangent bundle of X at that point P. And so it's not so hard to compute what the weights on this tangent space are. And so what that is, I'll just tell you, it's going to be 1 over 1 minus A times X squared times P naught plus 1 over 1 plus A times X squared times P1. And now I have to tell you what the third class is there. But again, so what I need to know is I need to know that, so EP3 of X, it's IP3 star of H times C3T of T of P of Z, because I'm embedding this in my smooth variety. That's my formula for using the embedding of the smooth variety. And so what this is just going to be, it's going to 2H here. The class is 2H, not not H. And so what this is, it's going to be, so H again restricts to minus AX on that point. So this is minus 2AX, and I have to take the product of the weights on this. So the weights are going to be 1 minus AX 1 plus A times X and AX. So what I get is just minus 2AX over 1 minus A times 1 plus A times A times X cubed. So of course this simplifies a little, and what I get here is I'm going to get plus minus 2 over 1 minus A times 1 plus A X squared times the class of P3.
So when you write H, you mean like C1T of O1 and O1
Yes.
natural linearization.
Yes, that's right. That's right. Well, now let's do an integral. Now that we've done most of the work for doing an integral, so let's do an integral. So what integral should we do? Well, should do the one that I did. Hopefully I can find it. So let's suppose we want to do the integral over X. So I want to integrate a degree 2 class. I don't want it to be too hard, but I want it to be a little bit non-trivial. So why don't we do C2 of T of PV? Just as a, I'm sure you could probably figure out how to do this some other way, but let's do this. This is kind of a proof of concept. So what this is. So let me temporarily call this phi. So what this is equal to I P naught star of phi of over 1 minus A X squared plus, and I'm pushing down to a point, so I'm just going to get this technically times the class of a point, that's uninteresting, but to be technical, I'll put it there. It'll be I P1 star of phi over 1 plus A X squared plus I P3 star of phi times minus 2 over 1 minus A times 1 plus A times X squared. Okay, now if the weights of T T of V are, this is just a representation of T, are beta 1, beta 2, and beta 3, then IP star plus C2 of T of V is just the second elementary symmetric polynomial in beta 1, beta 2, and beta 3. So these weights are easy to compute. If you compute them, you plug them in, what you get are 5 minus 3a over x squared times x squared over 1 minus a times x squared plus 5 plus 3a times x squared over 1 plus a times x squared plus minus 2 times 3a squared minus 1 over x squared over 1 plus a times 1 minus a times x squared. And this is all times the class of up point. Well, now, the good thing about this is that the x's all cancel out. This is a degree 0, and a is just a scalar. Now, this is supposed to be a rational number. So I did what we all do now is I put it into my friendly computer algebra system, and this is just 12 times the class of a point. So that integral is therefore 12. Okay. Now, the nice thing about this formula is that it's got a certain error checking aspect to it, because if you make a little mistake, you probably won't get a rational number. So I will confess that the first time I put this into the computer algebra formula, I forgot this factor of 2 here, as I did over there when I was writing. What?
Integer or rational number?
It's actually an integer, in fact, in this case. That's right. That's right. If I was doing a rational class, it'd be rational, but right, in this case, it's actually an integer. That's right. So it better be, in fact, it better be an integer. If we're merely a rational number, then I should also be worried. So anyway, that's a nice feature of this. Anyway, so that's the, and this basically boils down to the Bott residue formula. For a non-singular variety, the denominators here in these equivariant multiplicities are the terms that occur in the Bott residue formula. So this actually does boil down to exactly the Bott residue formula for isolated fixed points. Okay. And I'll just make one comment. That, like most of this stuff here, this doesn't depend entirely on the fixed points being isolated, because there's a general setup in case the fixed points are not isolated. So the general setup, if xt is not finite, but x is still smooth here. But now let's say x is smooth for simplicity. I mean, again, this wouldn't even, that even could be removed, but let's just say x is smooth for simplicity. So if y is a component of xt, then if I look at the top term class of the normal bundle to y in x, so this is an element in the T-equivariant cohomology of y, and that's invertible if I invert my elements in x, just for the same reason that for a point it was invertible, or for a slightly more complicated. So this is invertible in H star, in S inverse H star T of y. And I can write, we can still write x as the sum over all y contained in xt irreducible components I 1 over c, also c top t, say iy star C top and X, Y, class of 1. So we can still write this as a push push forward of classes on Y. Instead of what we've done is we've replaced the top Turing class of a point by the top Turing class of the normal bundle. And then the exact same argument will give you an integration formula just like before, except you'll be integrating over the components Y of the fixed point locus, which might be more or less complicated, but at least there's potentially smaller dimensional varieties than X itself. So you can get an integration formula that way. So again, many of these things, they don't really, certain things don't require the fixed point set to be isolated, but then things get more complicated. Okay, any questions? Okay. So I thought what I would do next is I'd explain a little bit about how these equivariant multiplicities can be used to determine topological information at the point, a possibly singular point of X. So topological from EP of X. Okay. So for what follows, I want to assume that X is an attractive. P is now an isolated fixed point. Of X. And in fact, since this is a local thing, I could even restrict to an open neighborhood and assume that P is the only fixed point of X if I want to. Since this is it's going to be a purely local calculation. So I'm going to assume, but for the moment, so I want to say that make the following definition. So even if X is singular, there still is a tangent space. And I want to say that, as you know, it's a risky tangent space. And I want to say that P is an attractive fixed point of X if all the weights of TPX T weights lie in half space, by which I mean there's some vector in the dual space, some vector V in the dual space, such that if I pair alpha with V, I get some positive real number for all weights alpha. Okay. So this is true for Fly varieties, because I'll just check it at the identity. The same thing works for any other point. So the point is that if X equals G mod D, then say T1B of X has weights, Xi minus Xj for I less than J. And so if I take V to be just the vector n minus 1 going down to 1, then any of these weights paired with V gives me a positive number. So all these weights lie in a half space. This is there since the tangent space to a Schubert variety is a subspace of the tangent space of the ambient Fly variety. This is also true for Schubert varieties as well. So they all have attractive fixed points. So T1 X is attractive, and the same for T of DB. Okay. So now, I want to state the following here, and what I'm going to do is I want to assume for simplicity, well, maybe I'll just tell you, make a definition here. So the definition will be that, so I'm going to put a finiteness assumption not only on the number of fixed points, but on the number of fixed curves. This assumption can be relaxed just as over here, but since I only have 20 minutes left, I'm going to put in this assumption. So X is a GKM space. If xt is finite and there are finitely many invariant curves, these are usually the same as one-dimensional closures of one-dimensional T orbits, curves from your closed curves. And each of these in the non-singular case will automatically be isomorphic to P1. So in fact, in all the cases, I'm just going to put that in as a hypothesis to P of 1. They will almost always be isomorphic to P1. If they're curves in a non-singular variety, then they will be isomorphic to P1. The fixed curve. So I'm just putting that in because there could be some kind of topology that might occur in some cases. So X, however, could be singular, like a Schubert variety, for example. And so I'll say if Tx on P1 is P of V via weights, say alpha 0 and alpha 1 on V. So there's an action on a linear action on V with weights alpha 0 and alpha 1. I'll say that we say Tx on P of V with weight, well, plus or minus alpha, which is where alpha is alpha 0 minus alpha 1. So the weights on the tangent spaces are actually alpha and negative alpha. So if I don't, unless I pick a point, I can't distinguish between them. So I have to put them both in there. In this case here, I'm going to actually be picking a point. So I'll be able to distinguish one of these and call that the weight. So if I can pick a point, then I can determine the weight. Okay. So if all the weights on P of X, say P is an isolated fixed point. And I guess I should say P1 or A1 here if it's if I'm looking at an open set, I don't want, maybe I throw out one of the fixed points. Okay. So if all the weights on TPX are, satisfy none is a multiple of another one. Then there are only finitely many and they're all non-zero. Then there are only finitely many T fixed lines in T of X. Because all the weights are distinct, they're all linearly independent, and so they're just one-dimensional weight spaces, and those are the invariant lines. Okay, so this is true for the flag variety. This is true for X equals B mod B, because the weights here are all the Xi minus Xj's, and none is a multiple of any of it. Okay, and So now suppose that X is GKM. And I want to give a condition. So when is X smooth at point P in XT? I want to give a condition on that. So there are only finitely many curves, T invariant curves passing through X. So there are finitely many C1 to CK or CN, well, I'll just say CK, invariant curves passing or through. So let's let cur P of X be the set of weights of these T invariant of these C's. They're really the weights of T of P C. So there's a so this is just some set alpha 1 to alpha n, right? Just some finite set of weights. And the theorem, which in the general setup statement, as I'm quoting, I think is due to Brion, but then for Schubert varieties, it had been discovered earlier by Kumar, was, so I'll just attribute it to in some slightly different language, is that, so let's let P be an attractive fixed point of X and assume there are finitely many. I'll just say assume that this is a finite set of weights, you know, the set of curves that P of X is finite. So there's finitely many curves passing through X. Then P is smooth in X if and only if EP of X is 1 over the product of the alpha in the curve P of X alpha.
Are you assuming the set of curves is finite or just the set of the weights?
I'm assuming really the set of curves is finite. I was trying, so that the set of curves is finite. Okay, so now let's apply this. Let's talk about applying this to Schubert varieties. So for Schubert varieties, so let's look at X, let's look at the point P of U sitting inside XW. How can we tell if this is a smooth point in principle? At this point, we have almost enough information to calculate to tell whether this is smooth. We know how to calculate EPU of XW. So now I just need to tell you what the set of curves is.
In the statement, you're taking the product over the set of weights, not the set of curves.
The way I defined it over here was it was the set of weights of curves.
So if there are two curves that have the same weights, that only
But
appears.
they can't have the same weight because the set of curves would be infinite. If two curves had the same weight, then there'd be two weights in the tangent space that were the same. And so basically, we would not expect that any sort of line in that subspace should give us an invariant curve. So we wouldn't expect that to be.
Okay.
So we can calculate this equivariant multiplicity as I've explained, and I'll tell you what the curves are as well. So the curve weights, a curve at PU of XW is a subset of the weights of TPW, TPU of X, the ambient fly variety, which is just what I described earlier. It's just U applied to the set of positive roots. Now, given any root alpha in U of phi plus, so alpha is xi minus xj, there's a reflection S of alpha, which is just the transposition ij, and that's in the Weil group, which is just the symmetric group. And it turns out that alpha is in per PU of XW if and only if P of the point F, when I apply S of alpha U is a point in XW. And that's equivalent to S alpha of U being less than or equal to W in the Brouwer order, which can be calculated combinatorially. So this is a condition for the set of weights to be for the first smoothness of Schubert varieties based on these equivariant multiplicities. So now we've gotten enough power so you can actually tell whether any point in a Schubert variety is a smooth point or not a smooth point. Okay. So in the last few minutes, what I was going to say, one thing I was possibly going to say, but it was that one can also get information about rational smoothness, which is when the Kazhdan-Mustu polynomials are trivial out of this equivariant cohomology picture. But instead, I think I'll just close with describing briefly what the image of I star is in the GKM case, and then saying how that giving an application to the case of toric varieties, which many of you may be familiar with. So the image of I star in the GKM case. So here we have xt is some finite set of curves pj, some finite set here, and if pi and pj are, if they're joined, if they may be connected by a curve or they may not be. If they're connected by a curve, Pij, let alpha ij denote the weight of this curve. And it's only defined up to sign, but that's not going to matter for what I'm talking about. Well, you can take plus or minus alpha ij, if you like. And the theorem is that, as I said, was that I star, and I don't know quite who to attribute this to. It appears in the paper of GKM, and there's many precursors that are also referenced in that paper. So I would probably attribute this to GKM, R.A. Chang, and Schubert. I'm actually not quite sure who to attribute this to, but it became very well known in the GKM paper in any event. So I star is injective, as I said before. And so we can think of I star, this is really the direct sum of I k star from H star P of X to the direct sum of the H star T of Tk. And this is just the direct sum of H star T. And the image consists of F1, F2 up to Fn. Each Fk is in H star of T, so it's a polynomial such that if Pi and Pj are connected by Cij, then alpha ij divides the difference Fi minus Fj. So that's a very beautiful description of the cohomology. In many cases, it's not, I would say, I think I can quote Fulton as saying once, well, it's unusual because we're usually thinking of rings as presented as quotient rings of things. And here we have a ring presented as a subring, which is, can be harder to do anything with. But let me just say quickly, this gives a very beautiful picture for toric varieties. So let me just say this very quickly and then I'll stop. So for toric varieties, let's say, and so let's say that I'm not actually sure whether non-singular needs to be in the hypothesis anywhere or not, but we can, for the moment, since there's 5 minutes left to my talk, I'll feel free to put in any hypothesis I want. So X can be a non-singular toric variety, but I'm not sure X, but it'll be complete. Associated to a fan sigma in the N tensor R, where N is the dual lattice to the lattice of characters. So assuming
In the GKM theorem, is it assume that it's X proper?
complete, yeah. So no, I mean, no, I don't know. I'm not actually sure whether X is. Let's say since there's 5 minutes left, X is proper here. X is complete. I mean, again, I think it's really only necessary that the cohomology H star T of X be free over H star T of a point, and that might, and I think that's probably all that's necessary actually, but that's why I'm saying if X is smooth and if it's a non-singular complete toric variety, then H star X is Tx is free over H star T of a point, and so that's why I wanted to just throw that in. So it's generated by a fan here. So here's our fan. It's got a bunch of cones, and then the way the inclusion. So every tau, which is a cone, corresponds to some subvariety v tau, and the correspondence is that it's reversing in that the maximal cones. So if tau is maximal, then v tau is just, I'll call it, say, p tau, which is just a point, or maybe I'll say maybe sigma is maximal. P sigma is a point. Now, so say this says, now if tau is a codimension 1, then v of tau is a curve with fixed points P of sigma and P of sigma prime, where sigma and sigma prime are the cones that contain tau. or whose closure, whose closure is taking tau. So say if this is tau, this would be sigma. Yeah, this is like sigma here and sigma prime is here. Okay. There's the curve, this curve, the weight of this curve is alpha, where alpha is there's a unique line in the orthogonal complement. So there's some alpha in tau perp contained in M tensor T hat tensor R. So N is the dual. So just to talk about this, N is the dual space of the co-characters T. So if I have a codimension 1 subspace of N tensor R, the orthogonal complement is a one-dimensional subspace of the dual space. In other words, it's a line. And there's some point on this line such that the weight of this curve is that point on this line. What else could it be? I mean, there's only one way to get it. And so these are the T-fixed points and T-fixed curves of this toric variety, which is a GKM space. So H star T of X is the set of all pairs F of sigma. So F of sigma is in H star T of a point, just migrating H star T, such that if sigma intersects sigma prime is tau, which has a codimension 1 cone, then the corresponding, I'll call it alpha tau, that's the corresponding weight, divides F sigma minus F sigma prime. Okay, now let's take a look at this geometrically on our fan. So if we look at our fan like this, I can restrict each. So this is the dual space. This is the dual space to the F sigma. So each F sigma is a polynomial function. So each F sigma is a polynomial on space N tensor R, because these are dual spaces, and so this is it's a polynomial, but it's in the dual space. So I can assign to every cone the restriction of that polynomial to that cone. The fact that the difference is divisible by alpha t, the zero set of this is the zero set of alpha t, or alpha tau. Tau is the zero set of alpha tau. So the fact that the differences are divisible by alpha tau implies that these two functions agree on the intersection of the cones. So F sigma restricted to tau is equal to F sigma prime restricted to tau. So what I get in this way is a piecewise polynomial function on the space here. It's polynomial on each of these regions here, and it's a continuous. So I get a continuous piecewise polynomial function. And so what we conclude by this GKM picture is the following theorem, is that H star T of X, the toric variety X associated with fan sigma, is isomorphic to PP sigma, which is the piecewise polynomial continuous functions continuous polynomial on every cone. So that's another beautiful application of the localization theorem. So I'll stop now. Thank you.
Questions?
Yes.
Sorry, this one example you were computing with the integral and the
Yes.
quadric, singular quadric, it seemed obvious to you that the result does not depend on A. Why is it obvious?
But, oh, right, oh, yeah, that's good. That was one of the things that I was gonna say. The thing is that H naught T of X is the same as H naught or of the point. Is this just the same as ordinary H naught of a point, which is U. And so there's again this forgetful map. And so this integral, this is consistent. Like when I push forward to this thing, it has to be sort of, like there's this kind of this.
A was rational there, no?
Well, it was an integer.
Yeah.
So what I would get is, I get like this, I get a forgetful map in the homology case, I get it as well to H naught T of H naught. And so here I have pi star of, let me put a T here to upgrade things. This is phi T intersect capped with XT. And this was here it was pi star of phi intersect X. And this thing has to map to this because I've lifted my classes. This is a rational number which doesn't depend on A.
Why?
Because it was a non-equivariant calculation. Phi was
Aha.
so it doesn't depend on. So yeah, that was actually one of the reasons. That was actually one of the reasons I put in the A instead of just making it a number. Is I wanted to show how it actually didn't depend on A, as your computer algebra system will tell you. Right. So yeah, it says, as I said, it's really it's these sorts of things involving localization. They're kind of bad in that. There might be many fixed points. Formulas are kind of complicated, but they're good in the sense that they have a certain amount of error checking involved. So at one point I was trying with collaborator, we were trying to compute the Schubert, some kind of multiplication in some Schubert things. And, we were getting that the structure constants were not, they were not what they were supposed to be. They were like quotients of things where they really should not have been quotients. And so we knew there had to be some mistake in the pullbacks. So when I got that number 12, I was pretty convinced that it was right. Yes.
So some of these results which tell you how to compute equivariant cohomology in terms of fixed point use this assumption that the cohomology is free as a modulo.
Yes.
So if I'm starting with my variety and I don't know the cohomology yet, and I want to use these results, is there some way to check?
Well, if X is in the paper of Gressy-Kaufman, first thing they actually give a list of 9 equivalent conditions for this to hold. However, I can only remember like 2 of them. But if X is smooth and projective, if X has vanishing odd dimensional cohomology, or if X in a more general case, if X is a Hamiltonian T space, so in the symplectic geometry world, it's actually also true. X is a Hamiltonian T manifold. So those are I would say, the main cases that you could know it automatically. So it's a pretty broad class, like for any smooth projective variety, it would be true. And that's like a theorem of deleting effect. So it follows from a theorem.
No more questions. Thank you.